I'm going to just record this a little bit. I'm recording it to the cloud, but there seems to be, I don't know if you guys have heard this or not. Maybe you know. There's a question as to whether or not when I record to Zoom's cloud, whether it stays or it goes away eventually, and I've got to download it. The nice thing about it staying is that I wouldn't have to keep the memory, and but I could always upload it too. You guys know if Zoom recordings get dumped? Probably haven't heard that yet. All right. Oh, here. If I do Zoom recordings, Brenda, in your case, if you don't want your face on the recording to be shared, then you could hide, stop video. But it is nice, I think, for people to see faces and stuff. So.
Okay, I can, it doesn't.
Yeah, okay, cool. All right. So Brenda asked a really good question. It's one that in my head I often am conscious of this, you know, the meaning of this saying that velocity is in a direction tangent to the path. Now this is a little tricky with one dimension. Let me start with one dimension. So if you're walking, and so one dimension might be that way. This might not be vertical. This might be north and south, and north and south is not, north is not that way. North is, let's see, where am I? Actually, it is pretty close to that way. North and south, where I'm oriented in this room. Not bad. So we have to know what we're talking about when we label these things. And one important thing, and this is, we're going to get there, is to not just jump to math and get an answer. That is not learning physics, and you will not be able to apply it to whatever field you go into at all. It's almost a waste of time. We want to think about the physics. What do these things mean? Maybe that's horizontal, maybe that's vertical, maybe that's not vertical. Maybe it's still horizontal, north and south. And another one-dimensional example is, again, an inclined surface. So if this is horizontal, then that's inclined. Now, let's talk about velocity in one dimension. So if an object is moving along that line back and forth, then tangent to a line is along the line. And so it could be going this way, and then could be going this way. And so the path is along that brown line there. So tangent to the path is on the line. Similarly over here, it could be going this way, and that could be a top view driving north or something, who knows? Or it could be vertical. But tangent to the path is either up or it's down. Along something moving along an incline, it's either going to be moving up or down. And that's tangent to the path. Where it gets interesting is two dimension. This extends, everything we do extends to three dimension. It's just messy, and you're learning so much so fast anyway that that there's no reason to go there. Let's see if I can do that a little more. Okay, so when we look at two dimension, which is something, you know, it could be a spider crawling on the blackboard. It could be so vertical, horizontal. And let me point out too, if this is my two-dimensional surface and something is moving along here, I could use coordinates like this, but I might use coordinates like this. And then I could either choose this way positive or this way positive. I could choose this way positive or this way. And this becomes a much more sophisticated use of math, making choices that fit. So if I'm going along an inclined surface, we're going to either choose this way as positive or maybe the other way. And we often choose perpendicular as a positive. We often say positive y, positive x. So I can cut up my two-dimensional space in any way I like. Okay. And I like to think of it as this grid. I even have a little piece of wire. That said, if a spider's walking on here, it doesn't care how you cut up, what you call X and what you call Y and which ways you call plus. But what is true is for that spider or for anything going in any two-dimensional motion, velocity is always tangent to the path. Let's take a look at that. And this is going to be important because in this book, one thing you can count on is that what I'm doing very differently than any other book is layering awareness and skills. And because, I mean, that's why people have such a hard time with it, because there's a lot. Okay, so here's my spider or whatever. I mean, it's Halloween, so. Oh, you guys, it's a blue moon tomorrow, which is in common since 1946. We use that term to mean the second full moon in a month. So if you get a full moon at near the very beginning, and you get especially with a long month, 31-day month, the second one is called a blue moon. It used to be called the third if you have 4 full moons in a season, but I won't go into it. Anyway, it's not blue. No, it's not the color blue. It's blue, which is Old English meaning betrayer. And if you were Catholic and you celebrate Lent, and that happens, that means you got to abstain from whatever for an extra month or something. So betrayer moon. Now you know.
That's cool.
Yeah, so you got to take my astronomy class. My astronomy class is actually descriptive, so no math, which for some of us, it's like I'd like to teach a class using math, but there's a lot to learn with it. So it's fairly straightforward for you folks. For you folks that know how to think like this, but for a lot of folks, it's challenging. Let me see if I can get rid of some of that glare. Okay, so here we go. So I've got my spider. I guess I should draw it below. I got a blue spider. And it's walking some direction along some path. So it has muddy feet. And so let's say the spider walks like this, and it could stop, sit there and eat a fly or something like that. I don't know. And it could go anywhere it wants, it could even, I'm not going to cross it because it gets a little confusing, but all right, I'll cross it there. All right, so there's the spider's muddy feet. That's its path. Now, if I have a movie, then I know what happened. But even with that movie, I can pause it at any point. If it's sitting there, of course, the velocity is 0. But if it's moving, velocity is the speed and the direction. We're going to get into vectors. So again, we're layering the ideas. But if it's going faster, I make a longer arrow. Sometimes we actually measure the arrow and say, okay, 10 miles an hour is going to be an inch, 20 miles an hour, 2 inches, and that's how I'm going to draw it. So you can do that. And we do it a little bit, but all right. So if this spider is moving, like when it's here, tangent to the path, again, the way that I think of it is, it's the direction if you're driving a car or running and you hit mud or ice that you would go. So the velocity would be here. And the longer I draw it, the faster, but I just say V. And so right here, tangent to the path would be this way. And I'll show you a nice way to think of that. So if it's moving along this path, wherever it is, and so here, when it goes this way, it's that way. And then here, when it goes this way, it's going down that way. And so you can imagine it just being a line that goes along the path. And so that's the direction. And this is an important point. It's a good question, because we're going to get into Newton's laws in chapter 7 and 8. And so if you, again, hit ice, that's the direction you would go if you were moving and you just went straight. So at that moment, you are traveling that way, but you're changing your direction. You can't change in an instant. You cannot change in an instant, but you can be changing. So when you pause a picture, its position can't be changing in that instant. I mean, sorry. When you pause a picture, it cannot change, but you know it is changing its position. It's a funny idea. It actually gets, especially people that aren't so much into math and stuff, it gets them kind of confused a lot. Does that make sense?
Yeah, so basically it's just the instantaneous velocity.
Yeah.
But when you're drawing the arrows, are they just showing what direction the velocity is going, or does it have anything to do with the value of velocity?
Yeah, the value would be like, if I draw it shorter. So, and this is an important point too. So sometimes we do just kind of rough get a sense. So you do really want to, be able to show, like, usually going into a turn, you'll slow down, go slower. And then maybe, going slow, and then come on over here, you start going faster. So you kind of draw it to illustrate slower and faster on a rough sketch. You can make a scaled diagram. So you literally, if it's twice as fast, you make it twice as long. More often than not, we just do a rough sketch, but it really is good to kind of scale it a little bit. Like, okay, I can see from here, I'm going slow, and then I'm gonna, apparently this spider started going faster here. And so, yeah. And we'll get into that in chapter 5 more too. So the direction is tangent, and the length is how much is related to the speed. Now, I will say this other little point too, just to say it. It shows you how much there is to physics, really. People can make mistakes. It's kind of slippery. And textbooks try to, you try to think about, well, what's the best way to say this? When you know something and you're explaining it, that can be tricky. So you will see, and this is just a preview, instead of doing one-dimensional motion, we do two-dimensional motion. Some books will write V with a half arrow, because that's faster than writing that. Means the same thing. And that means that this has direction. Unlike, say, speed, which does not have direction, or time, you don't put an arrow over it, time. Energy does not have an energy, it does not have a direction. by our definition of it. And so we don't put an arrow. Little thing, but I, for a very good reason, especially seen, and I discussed this in chapter 7 and 8. I say this is the speed and that's the direction. And this is what that is. That is speed and direction. This is the speed, that's the direction. We'll get into that in chapter 5. Don't worry about it for now, because it'll layer in. And I make these choices very purposely to avoid very common misconceptions. And literally in textbooks, there's something that they write that's wrong. And if you think about it, I know I was frustrated. I used to get frustrated when a textbook or professor would say something. It's like, I'm missing it because that doesn't seem right. And I come to find out it wasn't right. They were just being sloppy. That's kind of frustrating. Good.
Yeah, that was my only like tiny question, but
It's a good one, but you see, it's important to ask those little questions. And then you might also, because I like me, it would bother me. I'm trying to get clear on this. Another thing that used to bother me is this, the Greek letters. So here's a Greek letter. And that's the lowercase, and the uppercase goes like this. And you spell that letter this. And then people would say, some people would say phi, and some people would say phi. And I didn't want to sound stupid, it's like, but I didn't really want to ask them either. Well, is it phi or is it phi? Well, it's Greek. It's a Latin-based language. It's pronounced phi, if you want to go there. But then, people, and it's not just English. I mean, Spanish, people that speak Spanish as first language mispronounce the Anglo pronunciation, so what, I suppose, but I like to say phi. And this one is like, if you think of a line there, you write it like that. And that is this. And people often say mu, but for Greek, it would be mu, like a cow. And it's good because it reflects, you're thinking carefully about things and questioning things. So it's good to ask.
I'm taking Probinstat right now, and obviously mu is one of the variables, and I've never heard anyone say mu.
I know. In fact, I went to this, I've checked it a number of places. Like, I mean, I knew it was true too, but I checked it at a Greek festival. I checked it in Greece, and it's like mu. They don't say mu, say mu, but everybody else says mu. It's fine. It's fine. It's just, it took the weight off of me. Like, okay, fine. Yeah. I just want to say it right, but I was going to say, oh, it's really cool though, when you go to Greece is, and I didn't expect this, didn't even think about it. You look around at the signs, and if you've done a bunch of math and stuff and you know the Greek alphabet because you run out of letters, and then you go, well, that's pronounced like an M, and that phi is pronounced like a f, an F, and then pi is pronounced like a P, and rho, which is like not that, it's got to be like curvy, is pronounced like an R. And you sound out the signs, you go, oh my gosh, I can read Greek, because sometimes the word then when you sound it out is kind of like an English word. That happened a lot. I was kind of like, wow, this is so cool. So anyway, one of the perks. All right, I'll stop this.